Hi there everyone. Today we're going to be looking at vibration and damping as they relate to FPV quads. We're going to be looking at how vibrations are generated, how they're stored in the resonant modes of a frame, and how that energy is eventually dissipated as heat. We're going to be looking at why it's important to try and minimize the amount of vibration that you have in your frame, and how you can go about doing that. So let's get into it. So to start with, we have to ask the question, why are vibrations relevant for us as FPV pilots? Now in FPV, we know that our spinning motors and props generate vibrations because they're never perfectly balanced, no matter how hard the manufacturers try. But aerodynamic effects such as buffeting or blade stall also generate considerable vibration for our mini quads in flight. And all of these vibrations create noise on the gyro signal, which can obscure the real movement of the quad in the air. And so we have to try and filter out these vibrations so we can get a really accurate measurement, really accurate picture of exactly what the quad is doing and how it's moving in the air. Now, the level of filtering that we have to apply to do that depends on the amplitude of the vibration and their frequency. In general, lower frequencies and higher amplitudes require more aggressive filtering. And that's because lower frequency vibrations are closer in frequency to the real movement of the quadcopter that we care about. In fact, typically when we're flying, frequencies below about 100 Hz can represent real movement of a 5-inch quad, and frequencies above 100 Hz we would consider to be noise. If we look over at the graph on the right, we can see that at low frequencies we have some phenomena that are due to real movement of the quad. So this big spike close to zero is real movement of the quad. And this small spike here is prop wash oscillation. So that's also real movement that we want to fight against. But anything above that is what we would consider to be noise. So it's noise being generated by the motors. There's a motor hump there and another one here and a third one up here. And also noise that's created by vibration of the quadcopter frame. And this spike here is a good example of a resonant mode of the quadcopter frame that's creating noise. So we need to get rid of this noise, and that means we need to add filters. But filtering, whether you implement it in software or in hardware, for example by soft mounting your flight controller, all types of filtering add delay, and that delay is mathematically related to how aggressive the filter is at removing higher frequency noise. Any filter delay that we add reduces the responsiveness of the quadcopter to situations like prop wash or aerodynamic buffeting and things of that nature. As pilots, we want the minimum possible delay between the gyro registering a change in the movement of the quadcopter and the PID loop being able to react to that change. And that means that we want the minimum possible filtering. But of course, if we lower the filters too much, we run into other issues like oscillations, flyaways, and hot motors. So we can't reduce the filtering to zero, but we do want to reduce it as far as we possibly can. And to give you an example, I've put up here my typical filter settings for a GEP RC Mark IV frame that I fly. And you can see that I have very little filtering on this frame. I've turned off all my low pass filters. I've turned off all the notch filters. I literally have a gyro RPM filter there, the RPM filter, the dynamic notch filter, and one D-term low pass filter. And the reason that we need a low pass on the D-term is because the nature of the D-term means that it amplifies higher frequency noise more than it amplifies lower frequency noise. So without a low pass filter, you end up seeing an amplification of higher frequencies with the D-term. And that's something that you need to fight against with a low pass filter. My typical filter settings are really very aggressive. And this is to minimize the delay that I was talking about. Please don't just jump straight to copying these filter settings. You do risk flyaways, smoking motors, destroying ESCs, that sort of thing. Please work up to this level by slowly turning filters off, increasing filter cutoff frequencies, and hopefully if you've got a clean build like I have here, you'll be able to get to this sort of level of filtering without seeing hot motors, flyaways, or oscillations. Now, increasing damping can help with this vibration problem. And the rate of the vibrational energy dissipation to heat depends on a few different factors: the amplitude of the vibrations, the frequency of vibrations, and critically, the damping factor, the amount of damping that the system has. The amplitude of vibration, which is what the gyro is reacting to, is determined by an energy balance. And that energy balance is that the average rate of vibrational energy generation, due to the motors spinning, due to all the aerodynamic effects on the quad, must equal the average rate of vibrational energy dissipation to heat. Because there's no infinite reservoir for vibrational energy. The amount of vibrational energy in the frame is very finite. It's quite small, in fact. And so we have to have that balance of vibrational energy in equals vibrational energy out, because we can't store it up anywhere. So I've done this little diagram to show you what I mean. If you imagine that this reservoir here, this barrel, is the vibrational energy that's stored in the resonant modes of the frame as it's vibrating in the air, then we have motors, props, and aerodynamic effects that generate vibration, and that is adding vibrations into this barrel. It's adding vibrational energy into the frame resonance modes. And then we have damping effects that dissipate vibrational energy as heat, and that's causing vibrational energy to leave the frame. And this damping rate, the amount of energy that's being lost to damping, is dependent on the amount of vibrational energy, the amplitude of vibration and the frequency of those vibrations in the system. And so what we find happens is that vibrational energy in the frame builds up until the rate of vibration dissipation, due to damping, matches the vibration generation rate. And I like to think of this like a big barrel of water. And if you the vibration generation is you just pouring water into that barrel. But there's a hole in the bottom of the barrel, and that hole is the damping effect. And so the more you fill up that barrel, the higher the water level gets, the faster water is flowing out of that hole in the bottom of the barrel, which is due to the damping. And at some point in that barrel, you reach an equilibrium where the rate at which you're adding water pretty much matches the rate at which water is leaking out. And so you end up with a stable situation. And that then is the average amplitude of vibrations that you would expect in your frame. Now, there are, of course, things you can do to reduce the vibration generation in your quad by using better balanced props, better balanced motors, and flying less aggressively so you generate less vibration from aerodynamic effects. And there are also things that can be done in the frame design to make a certain level of vibrations less of a problem by shifting the frequency of those vibrations higher, for example. But today we're going to be focusing mainly on how to increase damping. So what is this damping that is dissipating vibrational energy from the frame? The damping factor is the ability of any structure to convert vibrational energy into heat energy. And structures with low damping factors tend to ring like a bell when you strike them, because it takes a long time for them to dissipate that vibrational energy as heat, and in the meantime they're ringing and creating sound. Structures with high damping factors don't ring at all. Instead, they sound really dead, like a piece of wood or a car tire. All of that energy that you're putting in as vibrational energy is dissipated very quickly into heat, and so they don't ring. The vibrations don't continue for any length of time. And there are a variety of different types of damping that can be active in a structure, and I've listed the 4 that I think are relevant here. Viscous damping is vibration dissipation due to viscous forces within a liquid. And this is the type of damping that's used in car shock absorbers to absorb energy. The car shock absorber, it forces oil through a fine grid, and by forcing the oil through that fine mesh, it dissipates a lot of vibrational energy. Material damping is the inherent dissipation of a solid material, and every material has a different material damping coefficient. Something like a metal has quite a low material damping coefficient, and so metal objects tend to ring when you strike them. Rubbers and plastics tend to have a much higher inherent material damping coefficient, and so when you strike plastic or rubber things, they don't tend to ring. Frictional damping, which is also called Coulomb damping, is vibration dissipation due to surfaces rubbing past each other. And you can see here a sort of schematic of a surface. On a microscopic scale, all surfaces are very rough, and they sort of bind against each other, and those little peaks and valleys rub against each other, and little bits of the surface break off and grind against each other, and that dissipates energy, and that creates friction heating, and that's another way in which you can dissipate vibrational energy. And the final way, which is honestly not very relevant for our mini quads, is magnetic damping, which is dissipation due to electrical resistance that acts on eddy currents created by moving magnetic materials. And there are some wonderful demonstrations of people dropping magnets down copper pipes and then moving incredibly slowly because there's all this energy dissipation going on due to the action of electrical resistance on the eddy currents that are generated by those magnets as they fall through the copper pipe. I might put some links in the video description. So if we look at a standard quadcopter frame and we go back to this schematic of how vibration kind of works, we've got a source of vibration energy coming in, and that's coming from the motors and the props and the aerodynamic buffeting and all that sort of effect. We have a certain amount of energy that's being stored in the vibration of the frame. So as the frame is vibrating in the air, it has a certain amount of energy in those vibrations. And then we have two sources of damping. We have material damping, that's the inherent damping of the carbon fiber material, of the metal in the screws, of the aluminium standoffs, all those materials. And we have frictional damping, which is the interaction of those separate parts against each other. So the arms acting against the frame, the motors against the arms, all of those surfaces touching each other create frictional damping. And the more joints you have in a frame design, the more frictional damping you're going to have. And this is why typically frames with individual arms sometimes perform better from a vibration standpoint than unibody frames. By adding those extra joints between the arms and the frame, you actually create more surfaces where frictional damping can happen, and therefore you increase the amount of damping that the frame has. So what if we try and do some things to increase the amount of damping in the frame? If we can increase the amount of damping, then it's like drilling a bigger hole in the bottom of that barrel. More of the vibrational energy is going to be dissipated, and that means that less vibrational energy will end up being stored in the frame at any time. And that means that the gyro is going to detect less noise. And what Bob Ruge discovered was that if you add electrical tape into the frame between the arms and the sandwich plate on the frame, you can add more material damping, because the electrical tape has quite a high material damping factor because it's a soft polymeric material. So they have higher damping factors than carbon fiber, for example. Other people have reported that foam tape also works really well. Foam tape has lots of tiny air bubbles in, and the compression and relaxation of those air bubbles during vibration actually can dissipate a lot of energy as well. And that, again, is an inherent material damping property of that foam tape. Another method of increasing damping in the frame comes back to what I was talking about with individual arms versus unibody frames. By changing the way you mount your arms, you can allow slightly more movement of the arm without compromising the stiffness of the frame, and that can help you increase the frictional damping. And this is my apex arm mounting hypothesis that I posed a few weeks ago. I believe that the way in which the apex frame is designed and the way in which its arm mounts are designed allow slightly more movement of the arms relative to the frame than a typical arm mounting design, and that by allowing that extra movement, it increases the amount of frictional damping in that frame. If you're interested in that, there's a whole video on the vibrational performance of the Impulse RC Apex frame on my channel, and I'll link it down below. Another method of adding damping that I talked about in a recent video is by applying mechanical damping grease between the joints of an FPV frame. Now, mechanical damping grease is an extremely viscous liquid, and this means that it's able to dissipate a really large amount of energy with even very small movements of the surfaces that are in contact with the grease. Even a very thin layer of grease between the surfaces of a frame can greatly increase the damping of the whole structure. And I've tried to show in this diagram the way this works. So the grease actually probably reduces the amount of frictional damping that goes on, but what it gives up in terms of frictional damping, it more than makes up for by adding a large viscous damping component. So as those surfaces move relative to each other, it's shearing that grease. And the grease really doesn't like to be sheared. It provides an enormous amount of resistance to that shear force, and that resistance dissipates an enormous amount of energy as heat in the grease. So based on my experience, I wanted to give you my thoughts as to the advantages and disadvantages of these different damping methods. Now, tape, it's very cheap, it's simple to implement, and it can definitely provide significant benefits on some designs. Bob Rugi's testing has shown that. But it does have some disadvantages. And what I've found is that the results with the tape seem to depend on the frame geometry and factors that are quite difficult to control, like screw tightness. In some cases, tape seemed to make things worse on certain frames, particularly if you used too much. And that inconsistency is, I think, one of the real challenges with using tape for this application. If we look at the Apex arm mounting approach, that's obviously very good because it's zero additional effort for the pilot. It's purely done in the frame design. And we know that it can provide significant benefits on some designs. But it cannot be retrofitted easily to existing quadcopters, and it's definitely not compatible with every type of frame geometry that you might want to fly. If we look at the damping grease, I found that this is effective on many different frame designs. And it's actually really easy to retrofit because it will work on any frame. You just need to take the frame apart, apply the grease to the joints, and then reassemble. The grease also acts as a thread locker and a corrosion inhibitor for your screws, so it provides some ancillary benefits that might be useful to you. However, it does have a significant disadvantage, and that is that it's quite messy to apply because it's unbelievably sticky stuff, and it takes a little time to do it. And if you're not really careful, you can end up with thin layers of grease on other surfaces of your quadcopter that can collect dust and get on your fingers and that sort of thing. But in my opinion, grease definitely is the most reliable and consistent method of adding damping to a frame that works on any frame. But then the question comes, what grease should you add? And so I've been doing some testing of a few different greases. And what I found is that how you fly the quad is really important when it comes to doing these apples to apples comparisons. It's so important, in fact, I'm going to be doing a future video talking about how to do really good A/B comparisons with black box logging. But I've tried to make these as A/B as possible. So I've used the same quadcopter. I've used the Betaflight default PIDs and filters for all these flights. I've done a similar extremely aggressive flight style with purposefully doing lots of heavy prop wash moves like split S's, power loops, pylon turns, that sort of thing, to really try and bring out as much vibration as I possibly can. Remember, we talked about aerodynamic effects being a source of vibration, and so I've really been trying to get as much buffeting, turbulence, prop wash as I possibly can to really generate vibration into these frames. And we can see the three flights. We have no grease on the left. Then we have a grease that I got from AliExpress called XY2 mechanical damping grease. And then we have a PG44A, the Nia gel on the right, which I got from Newgate Simmons. Comparing the three charts, I think it's clear that the XY2 damping grease is better than no grease. And the PG44A, in my opinion, did perform even slightly better than the XY2, particularly at the higher frequencies. If you can't find Niagel PG44A, they do a 767A and a 774VH. I hope that you enjoyed this video. I now feel even better informed about vibration, damping, and how it all relates to FPV. If you've decided to experiment with adding damping to your quadcopter frame, let me know down in the comments what method you chose and what effect it had on the noise that you see in your gyroscaled black box logs. If you'd like to support me, please consider subscribing to this channel. It seems like a small thing, but it really does make a huge difference when I try to engage with people in the industry on these sorts of topics. That's all I have for you for today. So until next time, I wish you all very happy flying.